So these are the formulas. We have to see that of which formula fits into the thing. Like suppose we have integration of 1 upon x square plus 16, say. Then 16, it can be written as 1 upon x square plus 4 square. So out of this, you see which one fits. Obviously, this one fits. So we just put the formula there. So it will be 1 by 4, 1 by a. So 1 by 4 tan inverse x by a. So x by 4 plus c. So in case we just see that which formula fits in and we do the thing. In case it is in root, we put the root formulas. So these are the first 6 formulas we need to start with for special integrals. Let's see the exercise. I'll explain how to put the things there. So here, like 3x square plus x to the power 6 plus 1. These are indirect sums. These are sums based on integration by substitution first. So clearly you see 3x square. We substitute according to like whose differentiation is coming multiplied to dx in the sum. So here 3x square, we ask whose differentiation is 3x square. That will be x cube. So to solve this sum, 3x square upon x to the power 6 plus 1, we take x cube is equals to t. So 3x square dx is dt. So see this 3x square dx we have. So automatically this whole thing becomes dt and x cube is t, so this becomes t square plus 1. Now if you compare, this fits into again 1 by a tan inverse x by a. So a here is 1, we get tan inverse t plus c. But what is t? T is x cube. So answer is tan inverse x cube plus c. Fine. So if like in the next case we have 1 plus 4x whole square. So we can take 2x whole square and 2x as t right now. I have a better method for this, but right now because it's the beginning, I'll take 2x as t. In this I'll take 2 minus x as t. In this you should try and then I'll help you in the class. Rest of the sums, fine. So till 9 it is all substitution and you'll guess. If you don't get, I'll help you live there. But let me move to question number 10th now. This is the beginning of the chapter, you can say. This is like this is 1 upon quadratic or 1 upon root quadratic format. So basically if you see 1 upon root quadratic, 1 upon quadratic, 1 upon root quadratic, this is whole thing is there, it's written wrong. Then again 1 upon, if you open up quadratic. So this is one of the type. We have to tackle 1 upon quadratic. Next will be linear upon quadratic. I'll explain that once I explain this first. Let me tell you what we do in this. So let's take this example. Like first of all, I'll teach you how to complete the whole square. If you have x square plus say 6x plus something 10 or anything like that, and we need to write this in the form of x plus something whole square plus something. So what we do, like let us suppose that the question is this only. To make it more clear, I start with the example of 1 upon quadratic, and this is the question. The first job is to complete the whole square here. Huh? So we have x square plus 6x plus 10, which I can write as x square because it's a square plus 2ab plus b square. So we write it 2a and b. So you have to think what you should write here so that you get 6. 2 is already written, so definitely you have to write 3. Then you need a 3 square so that you get a square plus 2ab plus b square. But I can't put anything on my own, so I have to remove 3 square at the same time. The method that I am explaining right now is the base and is primitive way of completion of the whole square. I'll explain it in a different way, like I'll give you a shortcut immediately after this, but if I tell you the shortcut directly, you won't be able to understand properly. So first I'm giving you the reason, and then I'll explain or I'll tell you a shortcut which will make you very fast. So plus 10, that number was already there. Now you see this much is your x plus 3 whole square, fine, because it's a square plus 2ab plus b square minus 3 square, that is 9 plus 10. So minus 9 plus 10, that's x plus 3 whole square plus 1, which you can write 1 square. So this now changes to this. So what we do, in place of the quadratic we can write x plus 3 whole square plus 1 square, and you know that this is nothing but 1 upon x square plus a square again. So tan inverse x plus 3, because a here is 1. So 1 by 1 tan inverse x plus 3 by 1 plus c is your answer. So I was about to tell you that there is a shortcut for completion of whole square. So I'll explain that now. So say we have x square plus ax plus b. So this can be plus or this can be minus. The shortcut is that you see that your x square should be coefficient free, like there should be strictly 1. So suppose this is something else here, I'll divide the whole thing by that number. Fine, so suppose there is a 2 here, I'll divide throughout by 2. Keep your x square coefficient free. It should be only carrying 1. This is already 1 I have taken. So x square. Now see what is your coefficient of x. That's plus minus a. Plus a or minus a. Whatever it is, divide that by 2 mentally. Okay. Always divide that by 2. If it is plus, write plus. If it is minus, then write minus to x. And write this as whole square. Got me? Like see the coefficient of x, say a. Let's take one example side by side. Like suppose I have got x square minus 4x plus something. So what I'll do, I'll see coefficient of x here is minus 4, and minus 4 upon 2 is 2. So we'll directly do x minus 2 whole square. Then square of this number should be subtracted, always subtracted outside. So a square by 4 outside plus b. B was already there. So if I exemplify here, it will be x minus 2 whole square minus 4 plus 16. So that gives you x minus 2 whole square and plus 12, which you can write root 12 whole square and to match it to the thing. Fine. So this is the completion of whole square. 1 upon quadratic, complete the whole square. Fine, that will be the method. 1 upon quadratic, complete the whole square. Like next sum I see is carrying a negative sign here. 7 minus 6x minus x square. So if you have if you have 7 minus 6x minus x square, we'll take the minus sign common inside the root. It will become x square plus 6x minus 7. Now you complete the whole square the way I told you. So 6 by 2 is 3, we'll write x plus 3 whole square directly, and then minus square of this 3, that is 9, and minus 7 already present. So this gives me minus x plus 3 whole square minus 16, which we reoperate the negative sign, becomes 16 minus x plus 3 whole square. So 4 square minus x plus 3 whole square follows a square minus x square. So actual sum will become 1 upon under root of this 4 square minus x plus 3 whole square, and we can integrate that as 1 upon a square minus x square. If you see the formula sheet, it's going to give you sine inverse x upon a. Fine. So next set of sums are these, linear upon quadratic. In linear upon quadratic, see, these are all linear upon quadratic. What we do, linear upon quadratic or root quadratic. Okay, linear upon quadratic or linear upon root quadratic. First, I'll explain the bookish method, the method that is there in your course, in your book. In that, like if you have 2x plus 3 upon x square plus something 4x plus 10, suppose. This says that you have to write the numerator 2x plus 3 as a into differentiation of the quadratic quantity. So 2x plus 4 plus b. So you open this up, you get 2x plus 3 is equals to 2ax plus 4a plus b. Now you compare, so comparing you get 2a, the coefficient of x, is equals to 2, so gives you a is equals to 1. Now put the other equation is 4a plus b should be equal to 3. So you put a as 1 here, you get b equals to 3 minus 4, so minus 1. Now we put a and b back in this and write it here in place of 2x plus 3. So the question changes to a 2x plus 3 plus b whole thing upon x square plus 4x plus 10. We split it, we write a 2x plus 3 upon x square plus 4x plus 10 plus b, put the value of a and b in the next step, dx upon x square plus 4x plus 10. So a is 1, and you know, whenever the derivative, the differentiation of the denominator is numerator directly, like if you take this as t, you will get dt upon t, which is log t, or you can take t right now, you can take x square plus 4x plus 10 equals to t and realize that it's going to be log of denominator. So it's a log of x square plus 4x plus 10 when you integrate. You can take this as t to realize it, plus b, so b is minus 1, and we complete the whole square, so x plus 2 whole square minus 4 plus 10, so that is root 6 square. You see how fast is this with the way I told you. Otherwise you keep doing whole square completion and all, and there's no marks allocated for like steps, you know. The marks directly applies to this step. So it's fine to do. So we get the result. It's 1 upon x square plus a square. So again 1 by a tan inverse x by a plus c. So this is the method given in the books. Okay. But I'd like to explain this, that how, you know, like I don't see any use of this whole method. I have another one, like if you like, you can use it, and it's very pretty common sense. You'll also say, yeah, this is like pretty clicking thing. That's like this. So in my method, I'll say create the differentiation of the denominator in numerator. So what is differentiation of quadratic? Fine. So for linear upon quadratic, the method that I'll be suggesting is that create the differentiation of the quadratic quantity in the numerator by multiplying, subtraction and all that. Huh? So 2x plus 4 is the differentiation of the denominator. 2x luckily is already there. If it is not there, then also it's not a big problem. It's very easy to, I'll give you some example. This is right now 2x plus 4. What I'll do, I'll write in the numerator 2x plus 4 on my own, but it was 3, so simply do minus 1. Like basically I added 1 and subtracted 1 to create the derivative of this on top. Now you see all those steps are gone. It is directly 2x plus 4. Many teachers are like allowing this and they're doing this also because they realize the stupidity of the other method. It's pretty like time consuming, there's no point I see. So this we can split in as 2. Any new method which makes your process easy should be most welcome. But I don't understand some teachers, no, they don't allow you, like they take it on their ego or something. So x plus 2 whole square becomes 4, so it's like again root 6 square, and see it's ready. Now you can integrate this. This is directly log of the denominator, and this is 1 upon a tan inverse x by a. So this saves your time, but it's up to you totally. If your school is following a and b, follow that, I don't mind. So this is linear upon quadratic. It applies to all the sums, but I was saying that if it is not 2x, if it is not that easy, let's take something else like 3x plus 5 upon x square plus 4x plus 10, what I took. Now it is not 2x plus 4 directly. But what I'll do, I'll take the 3 common out. Okay. So this becomes x, and let me write it a bit far so that I can accommodate other required things. 5 by 3. Okay, so I took 3 common out. Obviously this becomes 5 by 3, you know. I need a 2x. So divide here by 2 and multiply by 2. So this also multiplies by 2. Now I need a plus 4. So we do plus 4 and we do minus 4 upon x square plus 4x plus 10. Now you see, if I open this, I get a 3 by 2, 2x plus 4 upon x square plus 4x plus 10, and this is 10 and 12, so minus 2 by 3 into 3 by 2, so minus 1. 1 upon x plus 2 whole square plus root 6 square. So see again the same thing. If you solve with a and b method, na, the method that I explained earlier, then your a will be 3 by 2 and b is minus 1. So that is also pretty funny to answer in the class. You do it this way, and you can, without finding out a and b, you can quickly say that a is 3 by 2 and b is minus 1. Will be a good thing to do. Next thing is partial fraction. Like these kind of questions. Huh? Now for partial fraction, you see, if you see a question number 1, x upon x plus 1, x plus 2. Linear upon quadratic can be applied. Okay, you can do it by that also. But third question cannot be done that way because it's linear upon cubical, which we don't know how to tackle that way. This is, you can see directly a formula only, 1 upon x square minus 3 square. But it's all given here to like make you understand how we apply partial fraction. So let me explain what is partial fraction, what is the application of partial fraction. Basically partial fractions this is not integration, first of all. This is part of mathematics, a way to calculate things, and we use it to integrate things. Fine. I'll explain. Like there are three type of partial fraction, but partial fraction only applies if degree of numerator is less, not even equal to. Degree of numerator should be less than degree of denominator. Then only partial fraction applies. Otherwise, it's not possible. It's not allowed to use partial fraction. It will give you wrong results. So let me explain what is the meaning of partial fraction. What we do actually. Type 1 partial fractions. So let's take some example like that sum x upon x plus 1 x plus 2. So this is the integral, but I told you that partial fraction is not integration. So I'll do what? I'll write this separately. X upon x plus 1 x plus 2. This is a upon x plus 1. Type 1 partial fraction, you should have linear factors here. X plus 1, x plus 2, x minus 3, all multiplied, but they should be linear. And degree of the denominator you see is more than the degree of numerator. Numerator is less. So you can split it as a upon x plus 1, b upon x plus 2. If there be more quantities, then c upon x plus 3, d upon whatever. As many factors, those many arbitrary, those many constants will be coming here. Now we'll find out the value of a and b by cross multiplying. So we cross multiply, we get x is equals to, now many people say we'll take LCM and then cancel. I don't do all that. I simply cross multiply so that it saves your time. So a, c, x plus 1 cancels when we cross multiply, we get a x plus 2 plus b x plus 1. And this is the equation frame now. Now open it and get equations is a long method. We can take, because this is universal fact. This is like, don't see the upper steps. This step created now is a universal truth. So you can put x as whatever you want and it will hold. Values of a and b will come same for different values of x. So what we do, we put x equals to something which makes our job easy. So let's put x equals to minus 1. Like I make this 0. X plus 1 will be 0 when x is minus 1. So this whole factor, whole thing goes. And we get a. We get a is equal to, by putting minus 1 we get 1 and minus 1 here also. So we get a as minus 1. Now let's take x is equals to minus 2. Then this goes and we get minus b equals to minus 2, that is b is equals to 2. Now knowing a and b, we put it back here, and instead of integrating this thing, we integrate these individually. So this will become a, which was minus 1, 1 upon x plus 1 dx, and b, which is 2, 1 upon x plus 2 dx. So see, you get a minus log x plus 1, 1 upon x plus 1 integrated is log, because log x plus 1 differentiated is 1 upon x plus 1. 1 upon linear is going to be log of that quantity, plus 2 log x plus 2. Coefficient of x all 1, so we don't have to divide by anything, plus c. So this will be the answer. So though this question can be done with linear upon quadratic also, but if I use partial fraction, then this will be the way. Clear? This is type 1. Type 2, you will get something linear, quadratic, whatever, upon like x plus 1, then one of the linear factors will have a square or cube, some power to it, then it's type 2. And it will break as a upon x plus 1, b upon x plus 2, c upon x plus 2 square. You can't make this x plus 2 x plus 2. Huh? You're thinking that most likely, but you can't. Huh? This is the reason is that x plus 2 and x plus 2 square, the LCM will become x plus 2 square, which is present here. So a, b, c can be found out that way. But if you write x plus 2 and make it a upon x plus 1 plus b upon x plus 2 plus c upon x plus 2, then x plus 2 won't make it x plus 2 whole square. Okay. And further b plus c will become one single constant only. So basically this is the way we break for type 2. Rest of the process exactly the same I taught you earlier. So you cross multiply, you get 2x plus 1 is equals to a x plus 2 square b x plus 1 into x plus 2 because one of the x plus 2 cancels, and c x plus 1. Now put x equals to say minus 1, get a. Put x equals to minus 2 and get c. And put x equals to whatever, like put 0, because now you can't vanish any two other quantities to get b. So put x equals to whatever you want. Let's take 0, and then you know a and c already. You'll substitute a and c, you'll get b. Now knowing a, b, c, you substitute back and integrate. While integrating, take care that this is log, but this won't be log. This is 1 upon x plus 2 whole square. So becomes x plus 2 raised to the power minus 2 to be integrated. Okay. So when you get ABC, substitute back and integrate each. This is type 2 partial fraction. Type 3. Type 3 will carry something in the numerator upon denominator will carry such a quadratic which you can't factor. Like x square plus 1, you cannot get the linear factors of x square plus 1. If you equate x square plus 1 equals to 0, you get imaginary roots. So those quadratic which you cannot factorize, they create the type 3 partial fraction. This is to be followed as a upon x plus 2 b into differentiation of the quadratic upon x square plus 1 plus c upon x square plus 1. This is modified form of partial fraction type 3. If your school says that no, you can't apply all these things, they have a little, like I'll just explain. It's a upon x plus 2 plus, instead of b into 2x plus c, they write bx plus c. That's the book method. But I don't see any difference. This is more easy for me because b comes and then I get the differentiation of this on top. It's directly integrable. It becomes log x square plus 1. And this is directly c tan inverse x. Here we have to solve this sum separately in a kind of like bx plus c, linear upon quadratic. We have to split and we get the differentiation created and etc. So whatever suits you can apply. I prefer this because this is the way I did in my time. But if your teacher says no, you can't apply, then simply apply this, doesn't matter. For us it's the same thing. So this is type 3. Again we cross multiply and same method. You can put x as minus 2, then put x as 0, then put x as whatever you want, and put like a and b or c, whatever two of them found out, put that back in the equation, and you'll end up getting the values of a, b and c. So we integrate each. Fine. Now let's see the exercise. It'll be more clear to you. So see, first is type 1, type 1, type 1, type 1. We factorize x plus 1, x plus 2, again type 1. Very important sum. What's the reason? 1 minus x square upon x, 1 minus 2x. Sixth is very important. Why? Because the degree of the numerator and denominator, if you open, are same. So you can't apply partial fraction directly. So what we do then? we have to do long division. We divide 1 minus x square by x minus 2x square. But again, I'll teach you a shortcut for this. See 1 minus x square, see the highest degree term, highest power term is minus x square. Highest power term in the denominator is minus 2x square. Simply do this, minus x square upon minus 2x square. Divide the highest power terms. So, this will give you the quotient automatically. Quotient is going to be half here. It's a good shortcut to get the quotient always. So you don't have to do long division in these kind of cases. So you get half. Now rest of the things you can split with partial fraction. A upon x plus b upon 1 minus 2x. And then you carry on the normal way. So this actually simplified the whole process. Otherwise it's a very nice tough sum. That's why it's important. If you do long division, you'll end up getting half. I'll show you. 1 minus x square. If I like basically that's minus x square plus 1. Now let's divide this thing by minus 2x square plus x. Opened it up. So you see I have to write a half here. Half into minus 2x square will give me minus x square. And then we get a x by 2. So change of sign cancels and we get a minus x by 2 plus 1. So dividend like 1 minus x square can be written as divisor into quotient, half into minus 2x square plus x plus the remainder. So plus 1 minus x by 2. So when we have this, you see this cancels, we get half. This part is linear upon x into 1 minus 2x. So degree of the numerator is less than degree of denominator, can break into partial fraction. That's my logic behind this. So we can directly get the quotient and write it, and again like you can get the answer very quickly compared to doing all this division and all. But then whatever suits you. So 6th is done. 7th, you see x square plus 1, type 3. This breaks as a upon x minus 1 plus bx plus c upon x square plus 1, or you follow my method. So consult the solution that I have given and apply this to 7th sum. Type 2, then I think you should try. If I tell you everything, it's not going to be a good thing to happen. So let's discuss something which is like you can't get on your own, new. Question number 18th. Again, most important sum of this exercise. Besides that, here like cos x upon 1 minus, so you take, they've already given, so it's easy. So come back to 18th only. In 18th sum, we have x square plus 1, x square plus 2, x square plus 3, x square plus 4 to be integrated. X square is equals to y is taken generally whenever everywhere x square coming up, so that we only use this for the purpose of partial fraction. So this gives you y plus 1, y plus 2, y plus 3, y plus 4. When I said only for the purpose of partial fraction, I meant that before you integrate, you have to put back y as x square. Now this is not exactly that you are integrating also or differentiating also that. So you won't write 2x dx as dy because it's not available in the sum. So again I tell you that quicker method. Y square upon y square is 1. Quotient is bound to be 1. And rest is partial fraction. So you can break it as y plus 3, b upon y plus 4. Now cross multiply and carry on. Try, otherwise I'll help you live in the class. In question number 21, Don't follow this hint, it's useless. It's very easy sum. You can write e to the power x as 1 upon e to the power minus x minus 1 and then solve. Okay, so e to the power minus x will go up and we'll get 1 minus e to the power minus x dx. So if you take 1 minus e to the power minus x as t, this is the derivative. So log of, so that will be easier method compared to what you take e to the power x as t.